In this video, I want to show you the 1.3.3 version of the TMC4671 driver board, focusing on how it can be used to build a steering wheel, I have just received samples of the full Open FFBoard TMC4671 kits from Elecro, and I will use them to explain how to connect them, configure the system, and what common mistakes to watch out for. If you want a set for yourself, check the description if they are still available when you are watching this. These sets are already fully assembled with the STM32F407 main microcontroller board and the TMC4671 driver. And they also include the terminals, the power resistor, extra headers, the jumpers, and also two heatsinks to place on the MOSFETs. Additionally to these parts, you also need a servo motor with a supported encoder and a power supply, preferably 48 volts with at least 350 watts. It depends on the motor. You may get away with around 300. Some users like to use 500. It is also recommended to maybe have a lab power supply with current limiting, so you can actually test it safely without having to use the high-powered unlimited power supply for the first startup. Additionally, a USB isolator module like this is also recommended because this whole system does not include USB isolation. So in order to protect your computer and other USB devices, it can be required to have a USB isolator depending on the power supply and overall layout you are using. This motor is a 130ST M10025 with a 10,000 PPR encoder, which is an incremental encoder and directly supported by the TMC. This is the recommended type of encoder because it can directly interface with the TMC chip, and otherwise, like BC encoders, for example, or SPI encoders, they would need to go through the main microcontroller. This is supported, but it adds a lot of processing overhead. So I would consider this an experimental function and instead, if possible, stick to either ABN incremental encoders or analog sine-cosine encoders. Now for the setup, we connect with the config tool. And in this case, it is already in the right mode. If it is not, it might be in the basic failsafe mode. That would look like this. Just nothing happens and it's in this mode. Then you change it to force feedback wheel mode, wait for the chip to restart and reconnect, and you see the force feedback wheel tab. We ignore this for now. In the Access tab, we will select the TMC4671 motor driver, change driver. We get another tab, TMC4671, and maybe a bunch of pop-ups. For the version, we select 1.3 ACS 724, 66 millivolt per amp, because this is the gain of these current sensors, 66 millivolts per amp. This ensures that some constants are set correctly and the current graph, and also on the Access tab, the power slider is labeled correctly with the actual currents. It might also show an calibration required pop-up. We can ignore this for now because we do not have motor power connected. So what we have to do now, we can already set the motor to 3-phase BLDC. If you select the wrong motor type and it's powered up, you might damage components. So make sure to select the right motor. This is a 3-phase BLDC motor we are using, and an ABN encoder with 40,000 CPR, which is 10,000 PPR. It depends what the motor and encoder manufacturer specifies. CPR is 4 times PPR. So if we had power connected now and the motor, when we apply, it would immediately start the setup sequence. If you do not have a motor set to none, then it will not do the setup sequence and you could safely power it up. But in this case, I will set this already to 3-phase BLDC and ABN, so it would do the setup the next time it is powered on. And we just save this and reboot. Let it reconnect, check if everything is set as we wanted. That looks good. Then we also go back to the Axis tab, check the power slider, which is currently set to 5.8 amps. For the first startup, it should be low enough so it doesn't trigger your power supply's overcurrent shutdown in case you are using a lab power supply with a limit, as I would recommend for the first time. But it also needs to be high enough so the motor can actually align. So I would recommend maybe 2 to 5 amps, somewhere in that range for these kinds of motors. It depends on your motor what it needs. And now we are already ready to connect the motor and power supply and do the actual first power startup. So first let's take a look at the encoder. In this motor there were complete cables included, not just the connectors, and I have already crimped some pin header connectors on the right signals. You will have several different signals in the encoder connector and you will not need all of them. The important ones are the positive 5 volt, the ground, or sometimes called 0 volt signal for the supply of the encoder, the A, B and Z, and sometimes called N phase of the encoder. In this case there are differential signals, so each signal has a positive and a negative. We are only using the positive ones because our TMC board has a single-ended input and is not differential on the encoder header. It has differential inputs on the analog sine cosine input, but this is not what we are using today. So then we have also a bunch of other signals, the U, V and W, sometimes called the Hall sensor signals, even if they are not actually Hall sensors in this kind of motor. We are not going to use them. The TMC does have a Hall sensor input for this kind of signal, but instead, because we have a high resolution incremental encoder, we do not need these kinds of signals. They are currently not used in the firmware, so there's no benefit in connecting them. So we connect it to the TMC like this. Next we have our supply phases for the motor, and this is the bigger cable connected to the inner connector of the motor, and this one has a PE, the U, V and W phases. These are also of course labeled in the datasheet, but here it doesn't really matter how you connect the phases. It's just important that you connect them to the A, B and C inputs, or outputs in this case, of the motor driver. Do not use the D. The D is a 4th half bridge just used for stepper motors. Next is the most important connection, and this is the power connection to the resistor and the power supply. We are going to use another terminal again, and I have already prepared a connector for testing. This just has an XT60 and the resistor connected to the right pins. The right pins in this case, they are labeled on the TMC board. We have the ground, which of course goes to the ground of the power supply or the negative voltage output. VM goes to the positive output of the power supply. In this case, then it would be 48 volts, the positive of the power supply. And the most important thing is to connect this power resistor between PB plus and PB minus, like it is shown here on the silk screen. The power resistor is responsible for dissipating energy which is generated when you turn the steering wheel. Because there is a protection diode between the power supply's input and the internal voltage. The internal voltage is actually the PB plus pin, so you can measure this, and the MSV input, so the input side of the diode. And this blocks current from flowing back into the power supply, protecting it from overvoltage, for example. For this you will need a soldering iron and a beefy cable to connect it, and preferably also some heat shrink to make some kind of connector like this. You will have to check for yourself how long you want these cables to be. It doesn't matter which way around you connect the resistor, it's just a resistor. It does not have a specific polarity, but please make triple sure to have these connections correct. The right polarity and the resistor is connected. Like this. So, resistor, positive, negative. And now we are ready to power it up if it is already set up. Now that we have our motor and power supply connected to the driver, we can do the startup. I have now connected the system via USB and opened the configurator again. On the access tab, I have set a power limit of around 7 amps. You might want to go a bit lower at first. It depends on your motor what it needs for calibration. In this case, I know it needs around 7 amps to even calibrate. So do not freak out if it fails the calibration. Maybe the limit is too low. And on the TMC tab, we have set our motor to 3-phase BLDC for pole pairs, because this is what it is. And an ABN encoder with 40,000 CPR. The pole pairs will be in your motor datasheet and the CPR in the datasheet of the encoder. Now we take a look at the voltage. We see internal voltage is 4.5 volts, just powered from USB. And the input voltage is 0 volts because our power supply is off. For the first startup, I would recommend using a current limited power supply with a low current limit. So in case there is something wrong, you do not blow up any components. In this case, I know that it is fine. So I've set it to 30 volts and 5 amps. And when I power it up, you will see the motor move a bit and do a quick calibration to align the encoder and electrical phases. Now it has done a little wiggle left to right to check the alignment. And if that succeeds, you have a graph like this. It does one ramp to align the encoder and then just a quick check. This is the flux graph. And now we will have a weak centering force on the motor. And this means it is running perfectly fine. We can save it. In case the limit is too low, so let's say we just put it at 3 amps and do the alignment again. You will see that just nothing happens really during the check, and it will try again and fail. This is just because the motor is not strong enough to succeed. This also happens if you have the current limit of the power supply set to low, then the voltage will drop and you will see a low voltage warning. So yeah, now we have the failure. The encoder alignment failed because it could not succeed the check. But the only issue was that the current was too low. Now we actually have a steering wheel connected and we are going to center it. Let it do the startup sequence, and usually it will not be centered. In this case, we can hold it centered and press the SW switch. This will reset the encoder count to 0, or we can use the set center position action and also recenter the steering wheel. Now it is centered in this position. But if you have an ABN encoder with an index and it is connected correctly, then you can also use the home with ABN index function. So if this is set, you can, for example, at startup, it would spin the motor until it hits the encoder index, do the calibration, and then snap back to the previously saved position. So now it is always just centered when you power it on without having to do the sequence manually. Pretty much the most important setting is how strong you want your steering wheel to be. And this is controlled by the power slider. The power setting also directly controls the current limit of your TMC. So you cannot turn it up too high or you will run into the current limit of your power supply. And what you are seeing here, 10 amps, this is not what you will see from the power supply. In fact, it will depend on the motor resistance and a stall condition, and the current from the power supply will in general be much lower. When you put the steering wheel into the end stop, which is when you hit the limit you have set here, which is 900 degrees, then you will see this kind of current in the TMC. So in this case, 10 amps. But only 80% of this is used by the effects. So in this case, 8 amps can be used by the game, and the rest is used by the end stop. So you still feel the end stop, even if you are in a really heavy cornering situation and the game sends full force, you will still feel the end stop. If you put it to 100%, then it's the same and you don't feel the end stop anymore. So in this case, you can reduce the intensity of the effects without impacting the end stop strength. So I would usually use the effects intensity to make it feel weaker in game if you want that temporarily without having to touch the power setting. It does not make the effects clip earlier, it just scales everything down, just like the power slider. Another also quite useful setting for tuning how it feels is the independent damper. So also called the mechanical damper in this version. When you have it completely off, the whole motor is very light. It just spins freely. But if you have a real car, the steering wheel will not be this light. And if the game doesn't add a kind of damper effect to it, then it might oscillate or just not feel very good. So if I add a spring effect, for example, then when I just touch it, you will see it overshoot a lot and spin around and oscillate, right? That's not really what you want. Most games do add a damper, but if you want it a bit heavier, the mechanical damper is always active and dampens the movement of the steering wheel. So when I turn on the spring now again, you'll see that it is not overshooting anymore. So for tuning effects, it can be helpful to know which effect is actually used by a game. There are different direct input effects, and the most common one is the constant force effect, which is actually just sending force data to the motor directly. We have the effects statistics window, which allows you to see the maximum force an effect has reached and which one was active after a game session. So for example, when I use the iRacing force feedback testing tool and enable the simple spring and select the Open FFBoard, we see that the spring effect is active, and we can also see the maximum intensity the effect has ever reached. So this can help you to visualize if an effect, for example, has clipped in-game or if it is scaled way too low. You can also see the live effect forces. So in this case, we have a graph for the spring. And I can also, on the other hand, enable the force spring instead. And this is a similar effect, but it uses the constant force instead of the spring. And now we see it is actually the black trace, and with the spring it is the blue one. For the constant force, there is a filter. At the moment it is completely off, and this can help you to really tune in how you want the game to feel, if you want it very sharp and detailed or smoother. Every game treats it a bit differently. Most use the constant force effect, but some are very spiky and have a low update rate, and that will feel extremely noisy on a direct drive steering wheel. So in this case, you might want to reduce the frequency of the constant force filter. And this has an interpolating effect. So when I move this is a very, very spiky force when I move this slider. And you can even hear this. And when I turn it off completely, it will be much, much brighter in the tone. Because now high frequency content is there and it is much, much sharper, and you will feel also every tiny bit of force in the steering wheel, which can be distracting in some games. It depends on what you want. Sometimes you might want a very sharp feel, sometimes you might want it a bit softer, and this filter allows you to tune this in how you want it. There's also a torque filter for the TMC itself. I would recommend not being too aggressive. This filters basically every force which is sent to the TMC. So also effects like the damper effect. And you do not want extra low pass filtering, which is too strong on this kind of effect, or it will get unstable. So this can just add a little bit of extra interpolation if you set it to maybe 1 kHz or 500 Hz, and make everything a little bit smoother without having to turn down the PIDs, which can have other problems. On the other hand, you also have a notch filter. I don't think a peak filter is really relevant, but maybe a notch filter might allow you to reduce a certain frequency, which gives you in your steering wheel a resonance, for example. But in general, I would just have a weak low pass in the 500 to 1 kHz range. So to really get the best out of the motor driver, some PI tuning is required. These PI values are used by the current control loop of the motor driver. While the default values are usually okay for these motors and testing, manual tuning can be used to minimize noise and significantly improve the reaction of the motor. There is an automatic function, the auto tune button. I would not recommend blindly trusting it, as it is still very basic and will likely result in less than optimal values, as it is also highly affected by sensor noise and the motor, but it may give a reasonable base to start from. At the moment, that function increases P until the current reaches a certain level, and then it increases I while pulsing the motor until the current overshoots a certain amount. And it is also affected by the sensor noise. So it may be improved in the future to provide better results, and manual tuning gives you more control. But let's take a look at what the auto tune would think a good tune looks like. So you have seen the initial ramp up with the P value, and then pulsing I until it hits a certain overshoot. And P is actually spot on what I would also do manually at 600. And with I, it resulted in 1340, which is also actually a pretty good value for this motor. I'm actually kind of surprised. When tuning this manually, you would use a similar approach, but for P you would listen to the motor to find a point where it starts to hiss noticeably. Maybe we can hear this on the microphone with a strong amplification. So I would start, for example, with a low value of 100. And we do not hear anything noticeably from the motor. But for example, a value of 1000, then you should hear it hiss. Now the motor is a little bit louder, and this would be too much in this case. So we would go down a bit again. Let's say 800. And it got a little bit quieter, but not much. And now it almost disappeared. And that's what I would consider a reasonable P value in this case. With the I value, it gets much harder, as you may not find a point where it starts producing noise, and it will just get sharper the higher you go with I. Here it can help to have, for example, a testing tool like the iRacing wheel check, and use the force spring because it produces very sharp spikes when you move the slider and have the constant force filter off. You should have this off for tuning so you can really see how the motor itself responds. And then you can tune in the filter back again so the constant force is not too sharp. And you can hear that it already sounds very sharp. This is what I would say a reasonable tune is. But you might be able to go even higher, or if you have a motor which is not as sharp, you might want to make it a bit sharper, so you go higher. Let's say 2000. And we do not notice any additional noise. But it does sound much, much sharper when you actually give it some torque. This is why you need to actually pulse the motor to judge how it behaves. So this is something where a automatic, improved automatic tuning function would really help, because usually you would want to tune for a certain current overshoot and stability. And this is just not something you can do manually this way. So I would tune this mostly to taste or until you see something weird happening. This video got significantly longer than expected, but I hope it gives you a good summary of the most important setup steps and how to use this system. Of course, keep in mind that the information in this video may become outdated when features in the software are added or modified. Relevant links for the project and how to get the hardware and software are in the description. And lastly, of course, I want to thank everyone supporting this project since the beginning on Patreon, and everyone in our Discord helping each other out. Consider subscribing to the channel and joining our community as well if you are interested in DIY simulator hardware.